Well, it's a great pleasure for me to have Johannes Royset or Royset today in our applied math seminar. Johannes received his PhD at UC Berkeley in 2002. And then in 2003, he moved to the Naval Postgraduate School, where he went through all the different stages and has been a full professor since 2016. And his focuses in research are in stochastic optimization, set valued and variational analysis, and statistics, and of course, at the interface of all these important areas. So enjoy.
Hi everybody, it's great to have this opportunity to talk to all of you. Of course, it would be much better to do it in person. Really enjoy visiting Montreal in the past, but maybe there will be another chance in the future. So what I would like to talk about today is optimization, and let's go back to calculus even, and think about the problem of minimizing a smooth function. And one of the first things you probably learned in calculus was take the derivative, set it equal to 0, and solve for x, and that will be provide some sort of solution of this minimization problem. In the multivariate setting, say you have n variable, a vector x, the story is the same. We will then have a gradient that we need to deal with, and we want to find points where the gradient is equal to 0. So this is all when we are in the smooth setting, when the function is continuously differentiable. This is all good. Of course, Lagrange made an important contribution to extend these ideas to the setting where we not only have a function that we want to minimize, but we also have constraints, equality constraints, fi of x equal to 0. So if all these functions are smooth, you can form what became known as the Lagrangian, which is kind of an average of all these functions with some multipliers, multipliers y. And then instead of solving that original problem, one can then deal with a system of equations that somehow extend this idea about taking the derivatives that equal to 0. Now it is the gradient of the Lagrangian that has to be equal to 0. And that is a useful thing that one can apply to obtain solutions of constrained optimization problems. Okay, so what happens maybe around middle of last century was that inequalities became more and more important in various applications. And think about, for instance, some sort of logistic problem. I have some warehouses, maybe a warehouse in Washington State and one in North Carolina. And these two warehouses, they have certain inventory, and we're going to supply 3 cities, San Francisco, Chicago, and New York, with a various number of units that are demanded in these cities. So now there's an inequality because we cannot go beyond the number of units that we have in the warehouses, although we don't have to use up all of them, but we cannot exceed the number of units that we have in a warehouse. And this can also be formulated as an optimization problem. But now, as you see here, it will then involve inequalities. In particular, these WIs, those are the inventories at the warehouses, and I don't want to exceed that, so I can't ship more out of a warehouse than that is there, but I can certainly ship less. And this shift to inequalities, I think George Danzig should get much credit for. When he was sitting at the Army Air Force office in the mid-1940s, and worked on various planning problems, including how to assign personnel to various tasks. These equalities as well as inequalities came up quite often, and he developed what we now call linear programming and associated algorithm and things like that. And what we see here is indeed an example of a linear program. Okay, so that is inequalities in more in a logistics setting, and it doesn't have to be logistics only. It can have to do with network routing. Say Google would have to route traffic from different users to their data centers and things like that. So there are many problems that will come in this type of form. If we move into another application area, optimal control, so imagine we have a dynamical system, and maybe this dynamical system describes, for instance, some objects moving through some sort of channel. And in these pictures, you can imagine, for instance, maybe here on the right, there are some blue targets moving down the lane. And we would like to stop or identify or detect the targets. And we, meaning this red arrow, we're going to fly around and attempt to detect these objects. So we can formulate these terms of differential equations and things like that. And in that setting, we will have to also face inequalities. Maybe this searcher, this sensor that is flying around looking for these blue arrows or blue trajectories, maybe that has some sort of limited capability. It cannot turn more than a certain radius, and he might have speed that must be in a certain range. All of this will introduce various types of inequalities that we will have to deal with. There are also the issue of non-smoothness. And a topic that is very important nowadays is training on neural networks. And neural networks, as you might know, is roughly of the following form. There's some sort of input vector that is passed through various type of mappings. Often there's a lot of affine mappings, but there also can be nonlinear mappings. And one of the nonlinear mappings that are commonly used is so-called a ReLU mapping, and that is simply this function f of x that is the max of 0 on x. So that is a function with a kink. It's flat and then it starts going up. So it has a non-smoothness at the point x equal to 0. So now usual differential calculus will go out the window, at least at that point. So you might wonder, but this function max of 0 on x, the non-smoothness only takes place at a single point. So, you know, if you're thinking in terms of measure theory, this would be a kind of a measure 0 point. So is this something that we had to worry about when we deal with differential equations, dynamical systems? You know, we often talk about things in kind of some sort of weak sense, and maybe we can ignore this point where we have the non-smoothness. Well, unfortunately, in optimization, that is not the case. And the reason is that typically where you have the kink, it might very well be the point that you're most interested in, say the minimizers. Just think about the absolute value function. The minimum of the absolute value function is, of course, a 0, and that is a point of non-smoothness. So we cannot really ignore the fact that we're dealing with functions that are non-smooth, and we sort of have to address it head on. I mentioned a little bit about constraints, inequalities, equalities, and they might be represented as an abstract set, C possibly. And I will argue that such a constraint is in of itself also some sort of non-smooth component of the problem. Because if I think about my constraint represented in terms of a function, the indicator function in particular, which is 0 if x is in the set and infinity otherwise. And of course, this is a very non-smooth function in the sense that it's not even continuous. So if I want to represent constraints using this indicator function, I will also be dealing with some sort of non-smoothness. Okay, one more application. So one thing that we have worked quite a bit on is how to find bad guys that are smuggling. So this is a map of Central America, and out of Colombia, for many, many years, have been a big problem with boats of various types that are leaving Colombia and going up to Honduras and other places in Central America with various drug loads. And there's been international effort to try to detect and stop this. And one of the efforts that has been going on for many years is to fly aircraft out of El Salvador. And this is where El Salvador is. And these arrows indicate where a plane might fly, and the black boxes where it might be searching for a potential smuggler, and then we fly back. And in such a planning situation, you will be facing a certain type of constraints naturally. And what is a little bit more complicated in this situation, that you're searching for something that is moving. So the smugglers will be moving. So there are various things you need to balance. We've got to figure out where you want to be. This kind of time and space calculations that need to be carried out. The story ends up that you end up with constraints of this form that you see on the bottom here. That is a lot of variables, and then is the 2 norm less than equal to a constant time another variable. So this is a type of constraint that you might face in these type of models, and it's also a type of constraint that you see in various type of layout problems. But the problem with the norm, or any norm, 2 norm in particular, is that it's non-smooth when you are at the origin. And this is just another example of a non-smooth function that you might face in practice. Okay, so to address all these challenges associated with non-smoothness, associated with inequality systems and things like that, variation analysis is the mathematical tools that have been developed over many years to address the situation. And you can think about it as an outgrowth of linear algebra, differential calculus, and real analysis, but with a focus towards inequalities and a focus of functions that might not be smooth and not well defined in any of the traditional ways we might think about functions. And what I was hoping to try to do today is to convince you that variation analysis is a very important tool when we're going to develop optimization theory, models, and algorithms. And optimization is in many different applications, as we have seen, both in statistics, in planning, in logistics, and all those areas can benefit from variational analysis. And for those people that really want to get into the details of that area, I will recommend this text by Rockefeller and Wetz. They really also coined the term variation analysis, in fact. Okay, so what we're going to do today is 3 things I'd like to get through. First, I'm going to talk a little bit about variational geometry, talk a little bit about subdifferentiability, and then about approximation theory. Okay, so let's talk first a little bit about the classical perspective. We know from linear algebra and other contexts the concept of tangent and normal spaces. So imagine, for instance, you might have a smooth curve. I'm illustrating that in this picture. And we have at a particular point, we know what the tangent space is and the normal space is. Okay, so this is all good if you deal with a smooth surface. But as I've argued, that is typically not the case when we deal with optimization applications. So we need to go beyond that to develop mathematics that can address more general situations. And the first thing that I'll introduce is what they call the tangent cone. So a tangent vector is defined by this some sort of ratio. So maybe you can think about the this is some sort of a like a derivative ratio type of thing. But why don't we focus on the pictures to see if we can make sense of what the tangent cone is. So if I'm standing at a point x bar here in the left picture, and the set is the gray area here. So what is a tangent cone point? Well, it's really the tangent space plus everything on one side. But this is indeed a point of smoothness of this boundary, of the boundary of this set. So in a way, this is not entirely surprising. But what we have done compared to tangent space is that we are kind of adding everything on one side. That allows us to capture the fact that on one side, we are inside the set, and on the other side, we are not. And that's exactly the situation that we have when we deal with inequalities. Moving to the middle picture here. Here, x bar is at a corner point. And now the tangent cone has narrowed. So it is a little smaller, but it kind of points in towards the set. It's a local description of what the set looks like. Okay, and the picture to the right, this heart-shaped set, let's look at the point x bar there. There, the local geometry of the set is sort of, if I've kind of zoomed in very closely at that, around that point, is really the tangents are really pointing almost all the direction except straight up. And all those directions then become the tangent cone. So the tangent cone is important, but in fact, there's something that is even more important, and that's what I call the normal cone. So let's move on to that. The normal cone, or more specifically, let's get started with the regular normal vectors. A vector v is a regular normal vector. If it forms more than 90 degrees, the inner product less than or equal to 0, to all tangent vectors. So maybe a picture would help us if I go down to the bottom here. On the bottom to the left, this is the same picture that we looked at earlier, and remember the tangent cone was the tangent space and everything pointing down. So if I want to be more than 90 degrees away from those vectors, I guess I had to point straight up. And of course, this is what you would think of as a normal. So there seems to be a very natural definition. If I move to the center picture, there we remember the tangent cone was kind of pointing in, tangent cone was pointing in to the set. So the normals are kind of fanning out a bit in more direction, again, staying more than 90 degrees away from the tangent vectors. Okay, so there's something in the middle of this slide here that is kind of a refinement of what I said initially, that I'm going to enrich what I call regular normal vectors with some additional vectors as well. And what are those? Those are the ones that if I go in the neighborhood around my point of interest x bar and look at the situation there, what type of normal vectors or regular normal vectors will I have there? And any limit of such regular normal vectors as I approach x bar will then be added to the set. So if you think about what I have up here, the regular normals with a hat on top, that is the situation at the particular point. Well, when I remove the hat, it is taking into effect what's happening on in the neighborhood as well. But we'll be saying more about that in the next slide here. Here, focusing on this heart shape set. So I'm interested in the point x bar, which is in the cusp here. And if I take normal vectors at points coming into that cusp, then I will have this arrow, I'll have that arrow, and then in the limit it will be this one. So this would be an example of a normal vector that is not regular in this case. So, well, this is a little bit of a refinement, but what is the purpose of all of this? Well, it's actually very important for us to be able to develop a robust concept that can handle shapes that are not very nice. So by having this kind of limiting definition, we will be allowed to do various operations and come up with calculus rules that are much stronger than they would have been without it. But at this point, I don't have time to go into all the details, but we're keeping these pictures in mind. I think what we have now, we have normal vectors defined in a particular way. And we can talk a little bit about when will these normal vectors be computable, how we can compute it, and things like that. But before I get into the details, let's bring in one last concept, and that's the concept of Clark regularity. So Clark regularity is to have a shape of a set at a point where this refinement that I talked about from regular to general normal vector doesn't matter. I will get the same if I look at the one with the hat and without the hat. Then I say that the set is Clark regular at that particular point. So in the particular picture that I have on top here, I don't have a regularity because indeed at this cusp here, I do add something when I do this limiting operation. Okay, so let's get into something more concrete and look at, for instance, what the normal cone of an affine space. So let's look at a set C, defined as X is satisfying Ax equal to B. So this is an affine space. And we wonder if I'm standing at one point in that space, what will be the normal cone? And of course, this is very well understood. In fact, this is just what we call the normal space in linear algebra, and it's given by A, like we have here. A little bit more complicated if you have a polyhedral set, so you don't only have equalities, but your inequalities as well. Again, one can develop a formula for it. You almost have all of that from linear algebra, and in a way we haven't gone too far from linear algebra, but at least we have a concrete formula for what the normal cone would be of any of the points in that set as well. So where it gets a little bit more interesting is when we want to try to deal with more complicated optimization problems, where the constraints might not be equalities of the linear kind, might not be inequalities of the linear kind, but much more general constraints. And it turns out that many constraints that we find in optimization can be stated in this particular form here, that we have a feasible set that is specified by kind of like a underlying set capital X, some sort of smooth mapping capital F, and another set D. And it's actually possible to develop what is a normal cone at any point of such a set. And the formula is given on the bottom here. There are pathological cases that we had to watch out for. And for that reason, typically one would like to assume some sort of a qualification, that basically some sort of an assumption about the local geometry about a set is expressed here. And it weeds out any particular trouble that we might have when we have the special odd shapes and things like that. So that ends my discussion about the variational geometry. The main takeaway from all of this is that the concepts of tangent space and normal space from linear algebra and smooth manifolds and things like that, those can be extended to address non-smooth cases. And that is really critical to deal with the inequalities and non-smooth functions that we have in optimization applications. But it is actually also very fundamental to develop ways of extending concepts of gradients. I started out by talking about, the good old concept of taking the derivative set it equal to 0 as kind of the bedrock of how one will solve optimization problem. When we now don't have smoothness, what can we do? We need to have extensions of the concept of differentiability. It might not be maybe as powerful, as potent as we might like, but if we can have some sort of generalization of concepts of derivatives and gradients, that will be for sure come in very handy. And that's what I call subdifferentiability. So let's talk a little bit about that. And it turns out the investment that we have made in variational geometry is now going to come in very handy when we're going to define subdifferentiability. Okay, so how can we move from sets to functions? The key concept is that if I have a function, I can always think about it in terms of its epigraph. And as this picture indicates, the epigraph is nothing but all the points on the graph of the function and above. And above, I actually can go all the way up to plus infinity. I allow my function to even take on the values plus infinity. And that's very important because, as I indicated earlier, maybe this function capture effect of constraints, where I'm going to use plus infinity to represent a particular infeasibility. I might even permit minus infinity as a possibility of a function value. So in a way, this goes counter to maybe what a classically trained person will say, well, we'd like to have real value function. No, we will have extended real value function in this discussion. And I'll show that we can actually handle that, and we can have calculus that can still work very well to deal with even such more general functions. Okay, if we embrace this epigraphical perspective, that we think about functions interpreted epigraphs, we suddenly are back to an issue of sets. And we talked about tangent cones and normal cones of sets. So we can use those concepts, but apply it to the epigraph of a function. And let's see how that can get us to subgradients. So subgradients will then be the extension of gradients to the non-smooth case. And here's the story. Imagine have a function, smooth, non-smooth, whatever it might be, and I'm standing at a point x bar where the function is finite. Now, a vector v is a subgradient of the function at that point. If I take v and minus 1, and that turns out to be a normal vector of the epigraph of the function. So in the picture here, imagine that I'm standing at this x bar, so I'm up here, this point here. I'm looking at all the normal vectors, and I indicated that with this black arrow, so all the normal vectors at that point. And what I'm doing by introducing this minus 1, I'm just simply sort of normalizing the length of them. And all those vectors here are then subgradients. You know, this minus 1, you know, why was it minus 1 exactly? Well, you can kind of convince yourself that that is exactly what you want if you just look at a simple case like f of x equal x squared. And to think about at one point, what would be the normal vector of the epigraph of this x squared function. And then you see indeed, this is the definition makes sense. Okay, so if I take the collection of all subgradients, I'm going to use this curly notation, which goes back to Terry Rockefeller that introduced this notation in his dissertation in the early 1960s. And the reason that we're using this notation is to distinguish it from a gradient. A gradient is just a single vector, right? But here, as indicated in this picture, there are many subgradients at this point. In fact, an uncountable number. So that is, we're now dealing with a set of subgradients, and I did note that by this partial f. Okay. So what can we use with these subgradients for? And now we can go back all the way back to Pierre de Fermat, and he was famous for more than his theorems. He even worked a bit in optimization. Although he probably only had smooth functions in mind, but he really came up with this idea that the derivative should be equal to 0 at a minimum. And in our more general setting of non-smooth functions, we still have the same thing, that if I'm sitting at a local minimizer of a function, then 0 must be in the collection of subgradients. And there's nothing that I left out of this statement. This function f doesn't have to be smooth, doesn't have to be convex, or any other properties that you might want to introduce. This is really a statement that holds arbitrarily for any function, extend the real value possibly. So the concept of subdifferentiability in that regard is very general and is a way for us to get away from smoothness and be able to state or characterize in one way or another optimality of functions. I mentioned convexity briefly. Of course, much can be said about that, and often optimization courses place a great emphasis on convexity, and there's good reason for it. Of course, convexity is really a dividing line in optimization between easy and hard problems. If you're convex, it's somewhat of an easy situation in some sense, where non-convex is fundamentally harder. In the same way as in other area of math, applied math, linearity is kind of the borderline between hard and easy. So linear and non-linear is really an important distinction. In optimization is convex, non-convex, kind of a parallel distinction that one can make. You might have an intuitive understanding what is a convex set. Well, the sets that I'm showing here on the left are examples of convex sets, while the ones on the right are not convex. There's some sort of hole, a missing interior, or some sort of cusp in and things like that, which will be examples of non-convex sets. Now, what about functions? Well, we again rely on this epigraphical perspective and say that a function is convex if its epigraph is a convex set. And that's really a game changer, because then we can say that if I have a minimizer x of the function, then Fermat's rule, 0 in the subgradients, is not only a necessary condition, but is also a sufficient condition. So that's important to keep in mind as we talk about these various characterizations of minimizers, that in the convex case, all of these statements can typically be made somewhat stronger. Okay, so what is a key thing in many areas of calculus is of course being able to compute derivatives. And the chain rule is one of the first things you learn in calculus, of course. How would that be in this case? It turns out there is still a pretty strong set of calculus rules that one can bring in to compute the subgradients of a composition, say H composed with F, where F is smooth and H is potentially non-smooth. It might even be extended real valued. Then one will have a rule that looks very similar to the typical chain rule. Okay, and the chain rule comes in very handy to apply to various types of composite functions. Because typically in application, you will get the bits and pieces of your problem. Maybe there will be an objective function that you want to minimize. There might be constraints that you need to deal with. But that can be viewed using an indicator function as a sum of the original function f and then the indicator function of the set. So now the question is, what would be the subgradients of such a sum? And that, of course, would just be a special case of a composition. So the whole point of using this type of chain rules to compute subgradients would be to try to bring forward whatever nice structure that you have in your problem, being smoothness, convexity, that could be hidden somewhere inside, but it can be brought forward in a productive way. Okay, so now we're in good shape. We can apply these chain rules to compute subgradients of quite complicated, involved cases. For instance, optimization problem looks like this. One can cook up subgradient using the Fermat rule and come up with characterizations of local minimizers, for instance, as given here. And this is an example where the problem is not convex, it's not smooth, but still one can say something when the components are nice. Okay, so that was a quick introduction to subdifferentiability. Let's now talk a little bit about approximation theory. So when you face an application, often we have a problem that is not as simple as we would like. We might want to minimize a function f of x, but somehow it's not approachable. We might need to introduce approximations of various kinds. Maybe there's an element of sampling. Of course, that's a common thing in statistical problems. There could be some smoothing that needs to be carried out. You can think about discretization. You know, if we had been in an infinite dimensional setting, you know, maybe there would be a finite dimensional approximation. There could be linearization, penalization, other things that are brought in for computation or other reasons to try to deal with the actual problem of interest. And these approximations are going to indicate by f superscript nu. Again, even though you don't see any explicit constraints stated here, we are in the mindset that any constraints we might have are incorporated in these functions by assigning plus infinity when we are at an infeasible point. Okay, so clearly an algorithmic strategy now for solving the actual problem will be to try to solve the approximation as some sort of surrogate of the actual problem. And this might work very well, but it needs to be justified. There's also, of course, sensitivity analysis. There is almost kind of like a ground rule for all mathematical modeling of real-world situation is that one would like to have a model that is insensitive to small changes. If it's not, then it questions all the conclusions that you might draw from the model. You know, if small changes to the model somehow dramatically changes the output, there's big questions that can be asked regarding the validity of the model. So often when we like to do certain sensitivity analysis in optimization problems to try to identify if this is a suitable model in the first place. So that would also be an example where we can think about or would like to analyze an approximation of the actual problem. So now, what is an appropriate approximation in the context of optimization? Let's look at a cartoon here to illustrate a particular issue that might surface. And this has to do with uniform convergence. So imagine that you have an objective function f naught here. It looks like this, dashed line. And then have a constraint function g of x. And the problem I'm interested in is minimizing f naught subject to g of x less than or equal to 0. And it looks like this blue dot here to the right is indeed the minimum. Okay, but what happens if there is an approximation that is forced upon us? That is, g is replaced by g tilde. And this approximation actually uniformly good. So in the sense of uniform convergence, we might have that these g tildes are approximating uniformly to g. So that might seem like a very good approximation. But from an optimization point of view, it is not. Because if I now look at where the minimizer is. It's not over here anymore because that's an infeasible point. The minimizer is now here. So there was actually a large change in the minimizer, even though I seemingly change my constraint function only a tiny bit. So classical concepts such as pointwise convergence, uniform convergence, they're really not as helpful when we're analyzing optimization problems, at least not immediately, maybe not in the way we're used to in a classical setting. The right perspective from an optimization point of view would be again to look back at the epigraphs. The epigraph in this particular example that I just played with was kind of funny looking because we had a feasible point way out here that gave us a sliver of the epigraph out here. When we introduced the approximation, that sliver disappeared. So if you look at the epigraph here on the left versus the epigraph here on the right, they're quite different. So no wonder that the minimizers change as well. So it is really the epigraphical perspective that gives us the right insight. And this is where epi-convergence comes in. We say that a sequence of function epi-converges to another function if the epigraphs set converge to the epigraph of the limit. And set convergence is just basic saying that these sets, they start overlapping more and more informal. But the main takeaway on the bottom here is that if I have a sequence of solutions of the approximating problems, and those solutions are converging to some x bar, that x bar indeed solves the limiting problem. So if I want to justify my approximation, I can do that by establishing epi-convergence. So what is this set convergence more formally? Well, I have a slide here that defines what it is, and I'll skip over that in the benefit of time. But I could just give you an example of when we have this type of epi-convergence. For instance, imagine that you have a function f that comes down the black line here and then it shoots to infinity. While I have an approximation that is the red line dashed, that's always real valued. And at first it might seem that these two functions are nowhere close to each other. But if we look at what happens to the minimizers, for instance, the minimizer of the red is here. The minimizing of the black is here, and they're pretty close, and they get closer and closer as mu becomes larger, because then this bends up and moves to the right. And indeed, if I just are shaded in the epigraphs, you'll see that the epigraph also will get pretty close. So this shows that we can actually approximate a function that has plus infinity at certain places by a real value function. That's not a problem. In fact, it's something that we might use in a computational method to deal with constraints. And this is exactly the thinking, for instance, that we used in this search problem that I alluded to earlier in the talk, where we're looking for some targets. To justify approximations that are needed in this context, we establish epi-convergence, and approximations that are needed in this particular case is sampling, because there might be an infinite number of possible target trajectories, and one will sample the trajectories to reduce to a final number. And there's also approximation that has to do with that you're in function space, and you like to do computations using finite dimensional approximations. Okay, let's spend the last 5 minutes on set valued mappings and a little bit more details about this type of approximations. Let's think about a simple example, just the absolute value function. And the subgradient in that case looks like this. If I'm a negative point, then it's simply -1 as a, just a derivative. If I'm at x equals 0, I have a whole set of the subgradients. And then on positive values, I have, again, just a derivative. But what is striking is that if I look at these subgradients as a mapping from x to something, that something would be a set. So this is really a set-valued mapping that I'm trying to illustrate in this picture. That if I have an x, I don't produce a single point, but I produce a whole set of points. So that's, of course, what I call a set-valued mapping. And that's really something that we would like to deal with and will have to deal with, because subgradients are inherently not a single one, it's not a unique thing, it's something that we typically have a whole bunch of. In that context, again, we can try to say what would be a good approximation of a set-valued mapping. And that's where graph convergence comes in. So if I look at the graph of the set-valued mapping, maybe the shaded one is the graph of S, the gray one. And then it's the black hashed one here. That is the graph of S nu. And these arrows indicate that they're kind of starting to overlap each other. And that's what we call graph convergence, which is nothing but set convergence of the graphs. So what does that get us? Well, if I have a problem of the following kind, which I call a generalized equation, let's try to find an x bar such that if I put that x bar into my set value mapping, y bar is in that resulting set. And I guess the picture tells the story here. I have the y bar here, and I'm really looking at x's that kind of matches that y bar. And a prime example of all of that will be trying to solve Fermat's rule. Find an x that satisfies Fermat's rule will be a concrete example of that. So what is the main consequence of having graph convergence? Well, it's the following. If I have a sequence of solutions of the approximations of the approximating set value mappings, and these approximations converge to something, that something will solve the actual problem. So now we are in a possibility of develop kind of a general approximation theory for optimization problems. We have an actual problem, which is to minimize something. And then have an approximation is to minimize an approximating function. But these problems can be associated with their optimality conditions, just abstractly written in terms of set-valued mappings. So the actual optimality condition and approximately optimality conditions. And here are some examples, and we have alluded to some of them earlier. So suppose I have this type of approximations. What can justify that? Well, this is what I call consistent approximation. If the functions epi-converge and the set value mapping representing optimality conditions graph converge, then we have really justified our approximation scheme, and we can use it as an algorithmic foundation and solve the approximations instead of the actual problem. As a concrete example of all of that, let's look at the concept of smoothing. Let's just look at the picture quickly. So here on the left, I have a function that has a kink, because it actually consists of the max of two smooth functions. But that can be smoothed out, as I do over here on the right. The dotted line is kind of like a smooth approximation. And that is just one example where we have epi-convergence of the functions and graph convergence of the corresponding gradients and subgradients. So we indeed have consistent approximations and have a solid basis for solving the approximation instead of the actual problem. There's also an additional story that I don't know, I see that I'm 5'2" now, how strict are you on the time?
Five minutes to go.
Okay, 5 minutes, okay. Okay, so there's just 3 or 4 slides left. So what we have talked to up to now is how can I justify my approximation by making sure that in the limit, my approximation becomes more and more accurate, and in the limit kind of reproduces the actual function, actual problem. But we often would like to say something about the approximation error for any given approximation. And here's the essence, that if you tell me the distance between the epigraph of an approximating function and the epigraph of the real function, I can actually tell you something about the error in minimum values and in near minimizers. And a similar story for set value mappings when we talk about stationary points. So really the question of error analysis boils down to, can we compute this distance between these sets? And the answer, you can often do that using set distance calculus. And here is somewhat of an involved example of that, where I'm trying to address a real world setting where I have a lot of pieces. I have an actual problem, which is a composite nature. And there's an approximating problem, also a composite nature. And I wonder, if I take this F naught and replace it by F naught nu, and I know something about the error associated with that, how would that error translate into errors in minimizers? And a similar story for optimality conditions, which now can be expressed maybe something like this using the thing we talked about earlier. And again, will be replaced by various approximations. And of course, this boils down to how should I measure distances between sets? Well, there's nothing new about that. Pompeo already in 1905 and later on promoted by Hausdorff came up with ways how we will measure distances between sets. The problem with the sets we are often facing unbounded sets. And the Hausdorff distance it really works best for bounded sets. So it's, in our context, productive to introduce a truncation. So this d hat rho is really, think about it as a Hausdorff distance between two sets C and D, but there's a truncation going on, so I can handle unbounded sets as well. Whatever way I'm measuring let's skip that details of that and instead look at what one can get from carrying out such a thing. I said I was interested in figuring out the distance between the graph of an approximation and the graph of the real thing. Well, here's an example of what one can calculate. Well, that error consists of three terms, I guess. And each one represents the error associated with one piece of this composite function, being it a set, being a mapping, being some other function, being some Jacobians, or whatever it might be. So we can see how the errors of the various pieces translate into the error between the graphs, and the errors are then between the graphs are then in turn related to the errors between the solutions of the actual problem and the solutions of the approximations. But there's much that can be said. If anybody interested in that, here are two resources that can be helpful as the introduction to these concepts. And there's a lot of interesting possibilities to deal with optimization problems using these tools without feeling restricted to, say, to convex problems, to smooth problems, and being able to address many of the modern applications that we are currently facing. Thank you.
Okay, yeah, thanks, Johannes, for this very nice overview. A gentle tour de force, is if there is such a thing, through variational analysis, variational geometry, subdifferential calculus, approximation theory, epi-convergence, and set distances. We have time for questions. Warren has to leave. He says hi. But there was a question which I postponed to the end period from Kay Yang. Kay, do you want to unmute yourself, or I can also read the question?
Yeah, sure. So I'm sorry if it's too basic a question, but is it for all the variational things introduced today, can they be extended to non-Euclidean settings?
Yes. So I was dealing with many different concepts today, and one compromise I did with that is to deal with a finite dimensional setting. All the concepts that we talked about today can be dealt with in an infinite dimensional setting, and they have been dealt with in an infinite dimensional setting, and many of the definitions that you saw carry over immediately. For instance, things like epi-convergence, set convergence, they only require a topology. So it is very light concepts in that regard. What I talked about towards the end about quantifying the distance between sets, that require a metric. So you have to be in a metric space. But again, that will capture many applications. When it comes to subdifferentiability, the situation is a little bit more delicate. There, one has to be a little bit more careful how one would organize the thinking depending on type of space and things like that. But people have thought about that, and there are excellent texts written about the infinite dimensional setting. And I apologize, I didn't get into too much of that. I know the first reference that is up on the slide there does deal with infinite dimensional setting. So maybe that could be a place to look if you're interested in some of those things.
Yeah, sure, thanks.
Are there more questions from the audience? Please unmute yourselves. Aram has a question.
Yeah, sure. Hi, great presentation. I just have a question about, I guess, stochastic optimization problems. So is there like a natural parity, I guess, between, let's say you have like a stochastic problem where there's infinite data, so like a true expectation, and then you're basically taking the empirical samples. You have, let's say, n of them. And is that at all related to like an F superscript nu type setting where n goes to infinity, blah, blah, blah?
Yes, exactly. So so that would be, you can think about that Fn or F nu, that would be the sample average approximation using new samples. And the F would be then kind of like the true expectation. And that is all worked out. There are then a very general conditions under which you will have epi-convergence. And the conditions are very mild, much milder than, say, various uniform convergence type conditions. And the only thing you will need in that case, there's of course some measurability that needs to come in. And then there is a one-sided integrability, local integrability from below that needs to come in. But under those plus independent sampling, then you'll have a law of large numbers in the sense of epi-convergence. And I can direct you to a source for that, for sure. And that can also be extended further to have kind of a concentration inequality for that will quantify the error, of course, then with some additional assumption, some pointwise sub-Gaussian or something to that effect, then one will have that. So this is indeed a main tool to analyze stochastic optimization problems, and it can be done quite nicely dealing with very general cases.
Okay, cool, thank you.
More questions from the audience? I have one question. Actually, I have more questions, but one question in particular. So usually for the calculus to get off the ground, I mean, you either need some kind of clock regularity, or you need that you have a polyhedral setting. I mean, by polyhedral, I mean a finite union of polyhedra, something like that, right? But is there a middle ground where you see that some of these calculus rules could go through under milder assumptions? For example, all these constraint type of mappings, you always need the Clark regularity of the constraint set, which is just not, it's just not there many times. And if you don't have like polyhedrality or in the sense of Robinson or Clark regularity, I mean that the textbooks don't tell you anything, but maybe you have any.
Well, just look at the slide I brought up now.
Yeah.
Here, I think Clark regularity, it doesn't show up at all. The underlying set X only needs to be close, and in a way, the reason that we get away with our Clark regularity is because this H is larger than continuous convex. But I think there are, you know, if you go back, for instance, to the normal cone expression here, the normal cone expression here, this holds with an inclusion, as you probably know,
yeah.
Without regularity. So
but the wrong direction.
Well, that depends on which side of the aisle you are. I would say it goes in the right direction, but because it is an inclusion, it's a subset here, and not a superset, so it's a subset, and that in a way makes it larger, so you can state optimality conditions. And of course, there's a superset version if you deal with regular normals. So that will be, in a way, kind of works both ways, depending on if you want to switch to regular normals. So I think, yeah, of course, this is an issue that sometimes can be problematic, but what is a concern if you have something like a nonlinear equality constraint? Well, then it might be smooth, maybe, and then it's not maybe it's not a big deal.
Yeah, maybe a concrete question. For example, I give you a subdifferential map of a closed proper convex function, or a monotone maximally monotone operator more generally. Look at the graph. The graph's not going to be Clark regular because it's kind of an n-dimensional set in an n by n space, right?
Mm.
Unless that's polyhedral, what do I know about the, let's say, generalized well, smoothness property, or well, smoothness is the wrong word, but or regularity conditions of that set, for example? That's what kind of where my question comes in. But I don't want to put you on the spot. I just wanted to say, like, if you don't have Clark regularity, because that's ruled out by some underlying structure, and then beyond like the union of polyhedra, there's something missing. I have the feeling.
Well, let me give you a concrete example where I think things kind of work out satisfactory. For instance, we have the class of problems that are difference of convex functions.
Yeah.
So the f minus g, and both are convex. Yeah. So now you're in a setting that you're really dealing with, well, let's make it even simpler for ourselves. Say a function f of x that is minimum of 0 and x. So a minimum of 0 and x, and at x equal to 0, this is a point for the epigraph, which is not Clark regular. So you might say, well, some of this goes out the window. No, well, it's not a huge deal really, because you're right, at this point, you will, if you use this machinery, you will draw the unfortunate conclusion that x equal to 0 is a stationary point. But of course, x equal to 0 is not a stationary point, but it's very close to one. Of course, I mean, it's not a local minimizer, it's very close to one, because if I move a little bit to the side, then I will be at a local minimizer. And when you think about solving problems, numerically, one will have a little bit of a tolerance. So the fact that there was this one point where if you might use the kind of a little bit of tighter calculus, you would have been able to rule it out, but you use a more general calculus, the one I described here, and I could conclude that the point was stationary. It's probably not from a practical point of view a big deal, and the optimality condition that you get in this case are pretty useful in my opinion, and I think the simplicity of them outweigh maybe the potential small downside that it is a little bit of a weaker optimality condition that for instance those that you get by looking at directional derivatives.
Sure, yeah. I think we're going to stop the recording.